Hello everyone. In this tutorial session, we'll be looking into how to implement sequence alignment in Python. So the main package we are going to use in this tutorial session is called Biotite. And if you have not already installed it, you can install it using this command pip install Biotite. So Biotite is a library that gives us tools to work with biological data such as sequence data and structured data. So in this, I will provide a basic introduction into how to use this package. So we'll jump right away and we'll import the library. So we import Biotite, and then from biotite.sequence.io, which is basically the input-output interface, which will help us read the sequence files. So we'll go ahead and import those, and then I'll be importing some basic plotting libraries such as matplotlib. And then to specifically plot these alignments, I'll be using a built-in graphics submodule in Biotite called biotite.sequence.graphics. So I'll import that as well. So along with this tutorial, we have included two FASTA files, which is the FASTA file of ERP protein, and we'll be using this file to use, and we'll perform a sequence alignment between these two files. So let's go ahead and read the FASTA file. So FASTA file, you can be using the built-in function, you can read it as fasta.fastafile.read, and the path of the FASTA file can be given, which will automatically read the FASTA file. So a FASTA file is basically a text file that has been customized to represent sequence data, and it has a certain structure. So in the first line of the FASTA file, it should always start with a greater than symbol, which will indicate a comment. And this line can have any information pertaining to the sequence that is being present, or it could have other metadata such as when the sequence was obtained, and so on and so forth. So in this example that I've given, so we start, the first line contains a greater than symbol followed by the chromosome number and the genomic position, and immediately after the next line we have the sequence itself. And generally for each line, the formatting is done such that there are 60 nucleotides in or amino acids in a single line, so it will look much cleaner. And this is the main structure of the FASTA file. So two main points: a header that begins with the greater than symbol, and then from the next line the sequence starts. One important thing to note is that there can be multiple sequences in a particular FASTA file, and this is useful because you can represent multiple genes of an organism in a single file itself. Next, there is a built-in function called .items that will return all the sequence and headers that are present in a given FASTA file. So I'll print the first 20 headers in this particular FASTA file that I've read. So as you can see, the first header is SACEYAU, which is one of the strains of the yeast, followed by the sequence itself. And we see that it's present for around 20 of them, but totally there are 1000 of them in this in the sequence file that has been provided. And then now we just create a list of headers so that it will be easy for us to access whichever header we want, and then do the follow-up analysis later. So I'm using a list comprehension from this erp2.keys function, which will return all the headers of the particular FASTA file. Once that is done, we see that the first 20 headers are present here. If you were to give these headers, then you would receive the corresponding FASTA nucleotide sequence. I'll show how we can do that. So I initialize one variable called DNA-seq1 and DNA-seq2, and then from fasta.getSequence, you give the file object and then the header, and this will return the sequences pertaining to those particular headers. So we have DNA-seq1 and DNA-seq2. Notice that in this result there is something called an ambiguous equals false. This means that in this particular nucleotide sequence there are no ambiguous nucleotides. We know exactly what each nucleotide is. So, so we printed out DNA1 and DNA2, and now we will perform alignment. So, for alignment you have to get the biotype.sequence uh, submodule and then biotype.sequence.align submodule. So, if you recall your theory classes, then you remember that we need some kind of scoring matrix to score our alignments. This could be done by the use of a standard scoring matrix. Biotype has one of those built in. So, to return that particular scoring matrix, you use this function called align.substitution matrix, then standard nucleotide matrix. In fact, you can define your own scoring matrix as well. In this case, we will be going with the built-in standard nucleotide matrix, and I will just print the matrix to show how what it looks like. So, in the rows we have the nucleotides, and the columns are other nucleotides, and based on if there is a mismatch or a match, we have particular scores. You can argue that a nucleotide sequence can have only 4 nucleotides. So, what does all of these represent? Well, these are something called the IUPAC ambiguity scores. So, what an IUPAC code is that it gives a symbol to the ambiguity present. So, for example, if it's in a sequence, if there is an n, that means we do not know which of the nucleotide is present. So, it could be G or A or T or C. Or for example, if M is present, that means we are not 100% sure which nucleotide it is, but we are pretty sure that it's either A or C. And similarly, we have a code for each combination. So, that is what this combination refers to. And now, because I have just printed it, it is not very clear, or to get a better idea, we can actually plot it. So, what I have done is I have initialized a figure using matplotlib, and then a function called image show or imshow for short, and then I plot the score matrix. So, matrix.score matrix will yield this particular score matrix, and then I plot a color bar, and then I set the ticks. So, in this now it is more easily visualizable. So, the scores range from 5 to -4. So, if it is a match between A and A, then we have a higher score of 5, and as more mismatches come, we have a score of -4, and so in between all of them there are different scores possible. So, this is how the scoring matrix looks like. Now, we will perform the alignment itself. So, alignment is very simple in biotype. This is a function called align.alignOptimal from the align submodule, and all you have to do is pass in the 2 DNA sequences and the scoring matrix, and the rest of all will be taken care of by the function itself. So, one thing to remember is that more than one optimal alignment is possible for any 2 given sequences. So, I have run the alignment, and then now I will print the alignment. So, we are able to see that there is some matches, but it is not very clear as to where the mismatch is, or where so we would like some way to better highlight those mismatches. So, this is where the graphics submodule of biotype comes in. So, this function called plot alignment similarity based helps us plot these alignments in a more visually pleasing way. So, for this you need to specify the axis on which you want it to plot. So, that is initialized over here, and then the alignment itself, and notice the alignment will be a list of alignments. So, because as I said earlier, more than one alignment is possible. So, this will be a list, and you will have to choose the whichever element you want, and then print it or plot it. So, here I will be plotting the first alignment, then you provide the scoring matrix, then something called a color map, where you will specify what colors to use, and then show line position and show positions, just to give us an idea of where the mismatch is. So, we will just plot it. Yes. So, we see that for the most of the plots, most of the alignment, the 2 sequences are well they match each other, except for these positions where in the first sequence it's a T, and in the second sequence it's a C, and then in the first sequence there's an A, and the second sequence has a G, in the first sequence has a C, and the next sequence has a T. So these represents the coordinates of the sequence. So 648 is the length of the sequence itself, and there are 50 nucleotides in each row. So to get this position is it's basically 50 plus 37, so it will be so it will be 87. The 87th position has a mutation in which the T in the original sequence has become a C. So this is where how you can visualize the global alignment in the two sequences. Now we'll try local alignment. So from this itself you can see that the two sequences are not very different. So the local alignment would exactly look the same as the global alignment. So instead we'll be generating a random sequence similar to how we generate the random sequence in the previous tutorial for genome assembly. So again we use the numpy.mp module, and then we choose the alphabets that we need, and then we set the seed, and then using the np.random.choice function we create a sequence of length 102, and then we obtain the final sequence. So the two sequence obtained are this sequence 1 and sequence 2, and you don't have to have the same length of sequence, it can be different length as well. And then so to do local alignment, it is exactly the same as the global alignment, except in the function you provide this parameter called local equals true. By default it is false, so by default it will do global alignment, and if you want it to do local alignment then you can set it to true. And then max number is the maximum number of alignments you want the algorithm to return. As I mentioned earlier, more than one alignment is feasible for a given any two sequences. So now we have 5 alignments, and now again similar to the previous case we will be plotting them. In this case we'll try to plot all the 5 alignments together. So we initialize the subplots, the figure using the subplots function in matplotlib. So we'll initialize 5 rows and 1 column, and we set the figure size, and then we iterate through all of these axes, and then we plot each of the alignment in this axis. So as you can see, for the most part all of the sequences, all of the alignments are similar to one another, except here in some cases where there's a gap here, whereas in the next alignment there's a gap here, and so on. But what is important is that all of these alignments have the same score. And now we'll try with protein sequences. So if you have a DNA sequence, then it's very easy and almost trivial to convert into a protein sequence using biotite. So all you have to do is you have the DNA sequence, and there's a built-in method called translate, where and then you give this complete equals true. So this will translate the entire sequence instead of just searching for open reading frames and then translating only those. So you use that, and for the two sequences we translate them. So we have we have the translated sequence for the first protein and the second protein. So again we'll try this the same things with the protein alignment. So instead of scoring using a nucleotide matrix, we'll be using a standard protein matrix. In this case it will be BLOSSOM 62. So the we again initialize the scoring matrix as matrix equals substitution matrix dot standard protein matrix. This will automatically yield the standard protein matrix that is usually used in this module. So as you can see that we can see the square that shows how the alignments will be scored if there is a mismatch or a match, and again we will visualize this scoring matrix. Similarly, we initialize the figure, then using image show we show the matrix itself, and then we create a color bar pertaining to that image, and then we set the x ticks and y ticks and the labels. So now we have the scoring matrix. So as you can see, in the diagonal where there is a match, the scores are higher than when there is a mismatch. And the star represents a stop codon, and this X represents that we do not know what amino acid is present at that particular position. And exactly similar to how we did nucleotide alignment, we again use align optimal function, and instead of giving a DNA sequence and a DNA scoring matrix, we give a protein sequence and a protein scoring matrix. So in this case we get only one alignment, global alignment. We plot that alignment. So we can see that the total length of the protein is 216, and at these two positions there is a mismatch. And you can customize the color maps, the CMap option, to whichever suits your needs best, and less dark. So if you notice, this VA is less darker than KR, which means that this has a lower score than KRS. So we can see that so there is V and there is A, it has score around 0, and if there's K and then there is R, it has a higher score. So we'll now try the protein sequence alignments for the randomly generated sequences. So we have the sequence 1, which we translated using the built-in method, and sequence 2, which also we translate, and then we obtain the alignments using the previously used function. And now we plot all the 5 alignments together, and we can observe. We see that there are many gaps and many mismatches present, and also some matches. So there are the alignments are different, but their scores are, as I said earlier, the same. Now we'll be moving on to local protein alignment. So we'll do local alignment on protein. So similar to what we did earlier, all we have to do is set this local parameter to true, and the package will automatically perform local alignment for us. So in this case, we only have one local alignment in between the proteins, and then we'll visualize this alignment. So only this region of the protein are aligned to one another, and we can discard the rest of the alignments. So I hope you learned how to use the biotite package in Python to read and write FASTA files, and then to perform local sequence alignment. Thank you.